Okay, so that's time for Professor Sidoli. I introduce his curriculum. Nathan Sidoli received a Bachelor of Arts in Liberal Arts from St. John's College, Santa Fe in New Mexico, and a master degree and a PhD from the University of Toronto in the History and Philosophy of Science and Technology under the supervision of Alexander Jones. After postdoctoral projects in the Greek and Arabic mathematical sciences, working with Lennart Berggren and Ken Saito, he received an appointment at the School of International Liberal Studies, the Waseda University, Tokyo, where he is currently professor of the History and Philosophy of Science and Technology. His research deals with the Greek mathematical sciences and their further adaptation and development in Arabic sources with four main areas of focus. First, constructive methods in geometry, such as in the works of Euclid, Theodosios, and Ptolemy. Second, the geometrical methods of analysis and synthesis, such as in the works of Archimedes, Apollonios, and Pappos. Third, the mathematical methods developed in the astronomical texts, such as those of Aristarchos, Theodosios, and Ptolemy. And fourth, the translations and adaptations of the Greek mathematical sciences into Arabic in the 9th century, such as editions by Thabit ibn Qurra or the anonymous translator of Ptolemy's Analemma. He is the author of Thabit ibn Qurra's restoration of Euclid's data and the Spherics of Theodosios. He was formerly co-editor of Historia Mathematica, and he is currently co-editor of SCIAMVS. And the title of his Lectio is Approaches to Construction and Proof in the Elementary Geometry of Euclid and Apollonius. The room is yours.
Okay, thank you very much for that introduction, and thank you to the selection committee for the medals for considering my work in this way, and I would like to thank the leaders and the officers of the university and the organizers of the event today. It's really an honor for me to have my work recognized in this way, and especially considering the previous recipients of the medal. And it's a real pleasure for me to be here in Urbino today and to be able to talk about some of my recent work. Okay, so I'll try to stay close to the microphone. So what I want to talk about today is an argument that I have making, and it's going to be a fairly concise or sort of controlled argument in the talk. And I'm going to argue that, in fact, different Greek mathematicians were involved in debates about the nature of construction, and that these debates permeate down to the very basic levels of elementary construction and are almost certainly involved in debates that they were having about the foundations of elementary geometry. So I am going to use a theoretical framework that I developed for describing the constructions, and particularly the constructions and problems in the plain books of Euclid's Elements. This is books 1 through 6. Neglecting, of course, book 5 because there are no constructions in that book. And then I'm going to, in the second part of the talk, use that framework to analyze some problems which are attributed to Apollonius. And I'm going to argue that Apollonius is actually developing his constructions in a different way, and that this is almost certainly deliberately so. And we can see that there are different approaches to efficiency in both the constructions and in the proofs if we analyze them in detail. So first, in the first half of the talk, I'm going to outline or go over my understanding of the way in which constructions function in the element. And in particular, I'm going to developed this concept of talking about problems, constructions as they're used in problems, which I'm calling problem constructions, and constructions as they're used in theorems, which I'm calling proof construction. Now, there are some who claim that this is not a useful distinction for thinking about Greek mathematics, but I found that this distinction is useful for analyzing other mathematicians besides Euclid, and I'm going to apply this to analyzing Apollonius's construction today. So in this, and then I'm going to argue that the problems in Euclid's elements can be thought of as a kind of routine, which then calls in previously established problems as a sort of subroutine, as a kind of nested routine, and that this is done in a very specific way, which leads to the diagrams that we see in the manuscripts. And then in the second half of the talk, I will show that Apollonius takes a different approach to problems in three constructions that are attributed to him by Proclus. In particular, the construction for bisecting a given line, the construction for erecting a perpendicular from a given point on a given line, and the construction for constructing an angle congruent to a given angle, which is of course assumed as an axiom by Hilbert in his geometry. So it's very well known that the propositions of Greek mathematics are divided into problems on the one hand and theorems on the other. In a theorem, we have some assumed set of objects, and we make some mathematical claim about that object, and we show that it's true. It's sometimes the case, so for example, in 115, to prove that vertical angles are equal, that we don't need to introduce any further objects to make the demonstration. But most often, new auxiliary objects are going to need to be introduced. And these can be done through previously constructed problems, but there are also other sorts of assumptions that we can make. We can make counterfactual assumptions. Most famously, there's this assumption about superposition that is made in the congruence theorem and in the theorem in book 3, and so on. In a problem, on the other hand, we start out with some given object, and we show how to produce some new object using either the postulates and very often previously established problems. And then we need to show that this object that's been produced satisfies the condition. And this goes back to basically being a theorem within the problem in some sense. Sometimes we already have sufficient objects to get the demonstration done, but sometimes, particularly in more complicated problems, we're going to need to introduce further objects. And these can be done, once again, counterfactually and in various other ways, not just using the kind of routine of the problem itself. So this allows us then to distinguish between what I'm calling a problem construction and what I'm calling a proof construction. And what I'm going to argue later on is that Apollonius applies this distinction rigorously and moves as much as possible out of the problem construction into the proof construction. Another thing that I want to argue is that problems actually have a different structure. Euclid's problems actually have a different structure from the structure that Proclus gives in the famous structure that Proclus gives in his commentary, which everyone is familiar with. We don't see this in any of the problems of book 1, but we see it in the first problem of book 3, and I'll show it here. And I'm going to argue that actually Apollonius's problems all have this exact same structure, and I found it in other places as well, in Theodosios and so on. So book 3, proposition 1, is to find the center of a given circle. So somehow we have this circle, and we don't know where its center is for some reason. Somehow it's appeared without being drawn around a given center. It's just there. The first thing we do is we draw a chord in this circle. This is an unpostulated construction. We could reduce it if we wanted in some sense to taking some random points and drawing a line. It doesn't really matter. We take a chord. The next thing that we need to do is bisect that line. And what I'm showing here is all of the steps that would have been required to actually carry out that bisection using the subroutines. And I'm going to show how that works in just a second when we get into some of the detail. But that's it, that's the bisection there. But none of those dashed lines appear in our diagram. nor if we needed to use one of those dashed lines later on. So for example, notice that right through the middle of it is the diameter of the circle. It's already there, but we can't use that one that's inside those subroutines. We're gonna have to draw it again. And the way that we do that is we use 111 to erect a perpendicular from D to meet the circle there. And once again, we see the dashed lines, which are inside of the subroutine, but which are not available to us in the argument and never appear in the figure. And then we extend the line down using the second postulate. And then we're going to have to bisect that line that was already there when we did 110, but we couldn't use it. We had to produce the line itself. And then we're going to have to bisect that, and there it is. And that's F. That's the center of the circle. That's all that we need to solve the problem. But it's not enough to get the proof done. In order to get the proof done, we're going to have to introduce some other object. And we're just going to introduce any other object, any other point, and we're going to assume that it's the center. I'm not going to go through the proof, but we draw some auxiliary line, and we show that those lines, GA and GB, are not equal to one another. So this point G can't be the center, and this point G is any point other than F. So in the end, then, we can develop a kind of visual symbolism to encapture everything that goes on in this problem. We start out with some assumed objects, which I'm denoting with this kind of yellowish mustard color. And then we can introduce some objects that are auxiliary, which are the solid gray objects. And then in the background, which we never see, are the subroutine. And then we can denote the object that we're looking for in red. And finally, we have occasionally to introduce some new objects, and we can denote those in that blue color. So the overall structure then of a problem is we start out with a kind of given claim about what we need to do. We introduce the objects that we start with, and we give them some letter names. Then we carry out a series, a routine, which solves the problem. And then we're going to make a statement about what we need to show. And then we may or may not, but sometimes we're going to have to introduce some new objects. Then we do the demonstration, and sometimes there's a conclusion. Actually, the conclusions are quite rare in Greek mathematics. Okay, so just to give an overview, once again, we have a kind of visual symbolism that we can use. So this is 112, which is to drop a perpendicular from a given point to a given line. We see the given objects there in this kind of mustard color. And we have the auxiliary objects which are used, which are D in this case, and the circle that passes through F, D, and E. We see also the dashed lines, which are lines which never show up, which are inside of the subroutine. Finally, we have CH, which is the sought object. And in 112, this is the only problem in all of book one where there are any auxiliary objects, that is, objects that are only needed for the proof and don't have any function in the problem itself. Okay. The next thing that I want to argue is go into some detail about what I mean to say that a problem consists of routines and then subroutines, when previously established problem is called into a new problem. It functions as a kind of subroutine, as a kind of black box. So Euclid's problems are a kind of routine of constructive operation. They act upon given objects, and they return some new objects according to well-defined rules. You can also introduce arbitrary points in various ways. We saw some examples of that already. So new objects then are introduced or are produced through the postulate, the first three postulates, or they're introduced through previously established problems. And when they're introduced through previously established problems, this functions as a kind of subroutine. So all of the steps that are used in that previously established problem don't appear in that figure. They're black boxed in a certain way. And just as we saw in when we looked at 3.1, even though that diagonal had already been produced in 110, we couldn't use that diameter. We had to draw it again. And that's characteristic of Euclid's approach. Okay, so let's see how this works by going through the first 3 postulates and the first 3 problems. We can think of the first 3 postulates as constructive functions, which take some parameters, and they take as parameters arguments which are there in the figure, and they return some specific object. And often it's an object of a different type. It can be an object of a different type. So famously, the first postulate is let it be demanded to produce a straight line from any point to any point. We can think of this as taking 2 points, which are there in the figure, and it returns a segment between those 2 points. Actually, we could interpret this as a linguistic statement in a wide number of different ways, but that's the way it's actually used in the text. It's used to produce a segment, which goes from one point to the other point. The second postulate is to extend a finite straight line, so it's actually a segment in this case, continuously in a straight line. And once again, we could interpret this broadly in a number of different ways, just as a purely linguistic statement. So we have to see how it's used in the text to see how it functions. And it seems to be working as, we start out with one segment as one of the given objects, and then we have some other segment, which is an arbitrary length. It could be longer or shorter, but it is a segment. It's not a line or array that we're adding to it. It has some finite length. And we could do it, of course, repeatedly to get to extend it. But we start out with 2 segments, we end up with another segment, and the endpoint of one of our original segments is between the endpoint of the other segment. And the third postulate, of course, is to describe a circle about any point and with any distance. And we didn't go through the details of 112, but 112 has a point on the other side of the line, and we have the given point, and we draw through that given point and this around the given point and this newly introduced point, a circle. There's no line between those 2 points. There's no segment between those 2 points. It's just a span. It's a fixed span or a distance, diastema. So really the way that we need to interpret this is that we start out with 2 given points and we return a circle. It goes around one of the points as given and it passes through, its circumference passes through the other point. So this is actually quite different from the way that we use a circle, a compass. The first way that it's different is trivially different, which is that every compass has a maximum span. But these points are unlimited in the possible distance that they might be from one another. That's relatively trivial, I think. But the next thing is rather important, which is that a compass can always be used to set a pre-assigned distance somewhere in the figure and then just carry that distance somewhere else in the figure. Every real compass is of this sort, but Euclid's third postulate is not. So let's look at that in a little bit more detail. It's relatively well known in the history of mathematics that Euclid's way of introducing the postulate and using it in the first 3 problems involves this idea that we somehow can't carry distance around in the figure. We don't have a rigid transformation of length. So De Morgan famously called this a collapsing compass. I read recently in a relatively recent textbook of geometry, the authors call Euclid's compass a classical compass as compared to what they call a modern compass. But there is no such thing as a collapsing compass. And every actual artifact that we have from antiquity of a compass is just like a normal compass. You can carry the distance around from one place to another. So Euclid is working with a mathematical function of some kind. He's not thinking of the abstraction of a normal compass as a rigid transformation of length. Now that's in the solid book. He does that's in the plain book. He does in the solid book move length around in this way. He'll cut off a segment which is in one place of the figure from another place in the figure when they're not in the same plane and so on. And Huron and Theodosios do a similar thing. They'll have a segment in one place of the figure, and then they'll draw on a circle which has this as its polar radius, if you will, the segment. So there are a number of mathematicians who are thinking about the abstraction of a normal compass, of a real compass. And what I'm going to argue is that Apollonius is another one of these mathematicians. So let's look at the way that Euclid uses the postulates in the first three propositions. And this is going to make it really clear the way in which these subroutines are functioning in Euclid's construction. The first proposition is endlessly discussed in every text on Euclidean construction. Sometimes it's the only construction which is discussed in philosophical works of Euclid's construction, which is very unfortunate because it's actually quite unique in Euclid's way of approaching things. So what we want to do, of course, is construct an equilateral triangle on a given segment. We draw one circle about one end, one circle about the other end, we draw up the line, and boom, there it is. That's our equilateral triangle. And there are no auxiliary constructions in this figure that do not appear in the final figure. What we have there is just a flat routine made out of postulates. There is no previously established problems being used here at all. This is actually the only problem in Euclid text that is of this sort. Every other problem involves the application of previously established problems and therefore involves subroutines of some kind. And the second one is the easiest one to think about. So we can develop a kind of, I don't know if you want to call this a formalization or whatever, but a kind of symbolic way of thinking about this as well. So the first problem then takes a segment and it returns an equilateral triangle. So it's a kind of function in a certain sense. It takes one object, it returns a different object. They're not the same kind of object, but it's only one object that comes out of this. And it's a routine of 4 operations, and it's a flat routine in the sense that there are no previous propositions, so there are no previously established problems to use. And then, of course, we have to build everything from first principles. We have to build everything in the proof, everything from definitions, common notions, and so on, because there are no previously established theorems either to rely on. So the second problem then is that we have a given point and we have a given segment somewhere else in the figure, and we want to draw from the given point a line which is equal to that given segment. And so the first thing that we do is we join one of the endpoints of our given line to the given point, and then boom, we put an equilateral triangle on that line. But we don't draw it with circles. It just appears almost magically in the figure as a kind of subroutine. And those circles that are used in the background never show up in the discourse. They never show up in the figure. They're black boxed. It's a kind of subroutine, if you will. And then we're going to extend dA out. We'll extend dB out. We need to use postulate 2 a couple times to do that. We'll draw a circle around B passing through C, meeting one of the lines at G, then a circle around D passing through G, meeting the other line at L. And that's it. AL is the line that we're looking for. And if we look at it in the kind of visual symbolism that we've developed here, we see AL at the thought line. And really, there's only a couple of black boxed operations here that we don't see. So this is a relatively flat, series of operations. There's only a couple of missing elements, if you will. But the next one is not quite like this. And this is partly because this problem itself is so involved. It's so somehow complicated to bring a segment from one place in the figure over to another point. It involves actually altogether 9 objects there. So once again, 1, 2 can be thought of as a kind of function. It takes a point on the one hand, and it takes a segment on the other, and it returns another segment, which is congruent to one of our given segments. But actually, that AL segment is not just anywhere from that point. It's in a very specific location. And in fact, we could, if we wanted to use proposition from the data, we could prove that it's given in position and in magnitude. So the surface level routine of this is postulate 1, proposition 1, postulate 2 twice, and postulate 3 twice. But because of postulate 1 there, we have to open that up a little bit. If we were to actually draw this exactly as it's expressed in the text with a compass and straight edge, and we would end up with 9 objects to produce this relatively simple operation. An unstated corollary of 1, 2 is that we can draw a circle around a point with a segment which is somewhere else in the figure. This is, of course, the normal operation of a compass. And we're going to see that this is used in 1, 3. So in 1, 3, we have a ray, A, B, or it could be a segment, but probably a segment, but it could be a ray, either way. We're going to interpret it as a segment. And then we have a given segment which is less than AB, and we want to cut off C from AB. And essentially, it should be easy to do this if we had a compass. We just set it to C and then carry it over. But that's not what we do. We first have to draw the line AD. And in order to do that, we have to do everything that has gone into 2. So we see all of that in the background, including the 2 circles involved in producing the original equilateral triangle in 2. But none of this appears in the diagram. None of this appears in the text. What we have in the text is just AD hanging off of A, and then the circle drawn around AD and passing through E. And of course, that length, AE, is the length that we're looking for. But when we need to cut a length off of a lesser length off of a greater length, if we unfolded all of these subroutines, we would get all of these background operations there. Okay, so elements 1, 3 then is a function which takes, well, let's describe it as taking 2 segments and returning another segment which is congruent to the original segment. And E in this new segment will be between A and B. But this is, again, different from the way that we actually use a normal compass. And this is because in the construction, that line AD is given in a very particular place, whereas when you carry a compass from one place to another, the length is just anywhere on the circumference of that circle. So on the top level, Euclid's approach to this problem is very simple. We just apply 1, 2, and then we apply the third postulate, and then we have a very simple proof. But when we expand this and think about what's going on inside those subroutine, we see that there's actually 10 lines and circles involved in this. And this blows up really rapidly when we begin to get into more complicated constructions. So just as an example, this is the construction of a square on a given line, and it involves 35 to 30, I didn't count exactly, but mid-30s operations of lines and circles. And no one would ever draw a square in this way. Even a child in an elementary school could figure out a simpler way to draw a square than this. And it blows up in this way often because of the use of 1, 3, of cutting off a line from another line. Okay, so thinking of this as a characterization of Euclid's problems, we can recognize that Euclid is in fact not doing a number of things that modern mathematicians and modern historians and philosophers of math have accused Euclid of failing to do. So, for example, Euclid's problems are not a series of practical instructions for using a straight edge and a compass to work with lines and circles. They're highly impractical. They introduce triangles, rectangles, circles as fully formed objects. They don't introduce partial arcs and so on. Angles are bisected in full, lines are bisected in full, and so on. They don't show those constructions from the ground up in a practical way. They are also not lists of instructions for performing an optimal solution to producing the sought objects. They involve all of these auxiliary constructions, which are often not what we need to do. So this is, as you see there, the diagram is from a website that shows a simpler way to bisect a line than the one that Euclid gives. So obviously, simpler constructions are often overlooked in favor of constructions that call on previously demonstrated problems. The goal is to show the possibility of producing the final object. Also, as a bonus, when you call on previously demonstrated problems, you can use those properties immediately in the demonstration. But the demonstration then becomes more efficient. And we're going to see, in fact, Apollonius' demonstrations are less efficient than Euclid's. Finally, they're not a series of manual instructions for producing a kind of minimal graphic object that produces the final object. So they involve the introduction of these complete geometric objects. Previously constructed problems are introduced and used to produce something new. Now, as it turns out, we can see from Proclus's descriptions of Apollonius's construction that Apollonius's constructions involve, in fact, all of these things, which Euclid's constructions are not. So he's taking a completely different approach to construction. So in his late ancient commentary to the first book of Euclid's Elements, the Platonic philosopher Proclus sets out three alternative constructions that he attributes to Apollonius. Proclus also disagrees with all of these constructions because, of course, he prefers the Euclidean way of doing things. But nevertheless, we can find that there is a consistent methodology in these. In his descriptions of the problems 110 and 111, Proclus gives the full details of the construction provided by Apollonius, and he describes the difference between the way these constructions function and those in the element. This makes it clear that Proclus, first of all, understands that Euclid's constructions agree with the interpretation that I've just given of the construction. And it also makes it clear that he understands that Apollonius' constructions were different, that they were methodologically and consistently different. So by analyzing these in detail, we can develop an understanding of Apollonius' approach. Now, in fact, Proclus's discussion of 123, which is to construct a congruent angle, is not as clear. It's a little bit more difficult to interpret what Proclus actually means here. But I believe that underlying Proclus's description, we can find an argument which is in fact consistent with this methodology that we can develop, which is clearly and obviously set out for 110 and 111. So this is a slightly more conjectural, but I think that there is a kind of consistent methodology that was being used by Apollonius, and that this was then somehow lost in the transmission of this argument through the commentary tradition. It's almost certain that Proclus did not read Apollonius's text itself. He must have read this in previous commentaries that he read. Okay, so we will begin by looking at Proclus's commentary to Elements 110, which again is to bisect a given line. He says the geometer, that's Euclid of course, bisects a finite line using the first proposition and the ninth proposition in the construction and the fourth proposition in the demonstration. So this is exactly the way we would interpret Euclid as well. He shows that the bases are equal through the angles, so he's kind of sketching the proof there. Apollonius of Perga, on the other hand, bisects a given straight line in the following way. He says, let there be a finite straight line AB, which is necessary to bisect. We draw a circle around center A with distance AB again, a circle around B with the same distance. And let there be joined the line joining the intersections of the circle. This line bisects AB. And that's it. That's the end of the construction. And then the proof begins. For let CA and CB be joined. We introduce some new objects. Each of them is equal and common. Therefore, the angles are equal. And therefore, AB is bisected and so on. And then he says, sort of hand waving, something like that is the demonstration of the proposed problem according to Apollonius. He likewise takes the equilateral triangle. I think this is actually not the best reading of it, but sort of acceptable. And instead of taking the angle C as bisected, he shows that it's bisected through the equality of the bases. So his proof has to go to show the bisection of the line first, and we can see why that's the case later on. And then, of course, the proof by Euclid is better. It starts from first principles, it's simpler, and so on. So let's look at Euclid's proof in detail. We have AB, and we want to bisect AB, a given line AB, and we want to bisect it. First thing that we're going to do is put that equilateral triangle on AB. And again, the circles that are necessary to do that don't appear in our argument. And then the next thing that we're going to do is we're going to bisect that angle at C. And this is done through 1,9. And there it is. You see all of the background constructions to bisecting that. And that's really all you see in the end. You don't see, of course, any of the dotted lines. You just see the equilateral triangle with the upright. And that bisection is going to solve the problem. So D is the solution of the problem. But there would have been all of these auxiliary constructions that would have been necessary if we had followed the thing in exactly the way that's described in the text up to this point. So how is Apollonius' procedure different from that? He starts out with the same line. He draws one circle around one endpoint through the other, and then the other opposite circle. And then we have the 2 points meeting at C and D. And there, he draws the line, and that's it. That's the end of the construction. Actually, it's the same construction that we saw earlier, one of the modern commentators pointing out there's a simpler construction. It's the exact same construction. But there's not enough objects there to prove that the job has been done. We don't have any triangles in this figure at all. And we have no bisected angles. There are a couple angles, there's right angles, but we don't have the ones that are necessary. So in order to do this, actually Proclus's account is a little bit incomplete because we would have to use side-side-side congruence first to show that the angles are equal. And then we can use side angle side congruent to show that the bases are equal. So we'd have to draw these segments in here, and then we draw these segments in here. Then we can use side-side-side congruent to show that the two triangles on either side are equal. And then once we know that the angles are equal, we can use side angle side congruent to show that the bases are equal so that the line has been bisected. So then we can compare exactly the methodology of Euclid with Apollonius. And you can see that on the surface, and in many ways, in fact, Euclid's approach is much more elegant. It involves introducing two new objects, 1, and 1, 9. And then the proof is a one-step proof. You can apply side angle side congruence immediately. But Apollonius takes a different approach, and partly this may be because if we think about opening up the subroutines of 1, 1 and 1, 9, we get all of these extra objects which had to be introduced. So if we want a procedure that can be carried out with a straight edge and compass in a straightforward and easy way, Euclid's approach is not the best approach. So Apollonius's construction involves just 3 operations, 2 with the compass or introduction of 2 circles and an introduction of 1 line. And then he moves 4 lines into the proof. So the 4 lines that would be necessary to prove that the triangles are equal, to finally prove that the line has been bisected, are moved into the proof. And if we ever have to chain this construction with some other construction later on, we don't have to introduce those lines again. So you can see that we could be saving some steps if we're thinking about constructing rather complicated objects. So what happens here is that the construction becomes more elegant, but the proof becomes less elegant in a certain sense, because first of all, it has some constructions in it. Euclid proof doesn't need to have. And then secondly, because he hasn't introduced triangles as such, equilateral triangles as such, he has to prove that those sides are equal. So he would have to rely on the properties of the triangle, first of all, to prove that the sides are equal. So he would have to apply two congruence theorems as opposed to just one congruence theorem. We'll look at 111 and we'll notice that the features of 111 are exactly the same as the features of 110. This is what Proclus says. Apollonius produces the line at an upright, so in the following way. So again, we have a given line, a given point on it. We want to produce a perpendicular. Let there be taken on AC an arbitrary point D, and let there be set out CE equal to CD from CB. Let a circle be drawn with center D and distance ED, and again a circle on the opposite side with center E and distance, again, same distance, DE. And this should be FC, let FC be produced from F to C. I say that this is the line at an upright. That's it. The problem has been solved. It's over. But we have to introduce some new objects. For if FT and FE are joined, they're going to be equal. But DC and CE are also equal, and FC is common. So the angles at C are equal. Therefore, they're right. So once again, you see that this demonstration, which requires the drawing of circles, is more intricate than that of Euclid, because it's possible to draw the triangle directly on DE. In other words, just as Euclid did, we could just allow that triangle to appear immediately in our figure without having to draw those circles in. So Proclus seems to be understanding Euclid's constructions just in the same way as the theoretical account that I gave in the beginning. And then he says the rest of it is more or less the same. Okay, so Proclus gives a full procedure of Apollonius, but this time he doesn't give all of the steps of Euclid's procedure. We'll look at Euclid's procedure and we'll see what those steps are. We begin with a line and a point on the line. We take another random point on one side, and then we cut off from the other side of C a line which is equal to DC. We could do this with 1, 3. We could also do it with a circle, whatever. And it's the dotted circle there. And then the next thing that we're going to do is, of course, introduce that equilateral triangle. And then we're just going to need to join F and C. And that's going to be the object that we're looking for. And so there you see that, in fact, there aren't that many extra constructions that are kind of hidden in the subroutines here. It's a relatively sort of flat construction. But in fact, we'll see that Apollonius is still, once again, more elegant, just because of the fact that he's able to move some of these construction steps out of the construction into the proof. And this is the construction that Apollonius gives, and I'm going to make it so that the diagram that appears on the screen is the same as the diagrams that appear in the manuscript. And this is also going to make some implications for, I think, what Apollonius is doing, which are not made explicit in the text, but the diagram is going to end up being the same diagram. So we start out with AC, with AB, and given point C on it. We take a random point on D, D in the direction of A, and then we cut off another random point in the other direction, but the whole circle doesn't appear in the diagram. And because the whole circle doesn't appear in the diagram, I think this implies that Apollonius is thinking of the application of a normal compass, where we just mark off the point on the line. We don't have to introduce that entire object into the diagram. So now we have D and E there, and we are going to draw those circles in. The text says that we draw the circles in, but in fact, circles do not appear in the manuscript diagram. What we find in the manuscript diagram are semicircles. So again, it seems to be a minimal graphical construction of what's going on. It's not a mathematical function. in the same way. We draw the other circle in, it meets at F, and we join FC. And that's it. That's the final object. That's the diagram that appears in the manuscript. It's a minimal graphical construction. And then in order to do the proof, we're going to have to, of course, introduce some new objects. And so we introduce those two lines there, and then we will be able to show that we can use side congruent to show that the triangles on either side of C are equal to one another. The angles about C are equal to one another. So by definition, they must be right. Once again, we can compare exactly the methodology of Euclid's approach to Apollonius's. Euclid begins, as both of them do, by taking a random point. Then it applies, I guess, 1, 3, maybe it's postulate 3, a little unclear, but probably 1, 3, technically from the way the text is written. Then 1, 1, and then postulate 1. And the proof then is just side congruence, and then the definition of right angle. If we open the subroutine up, we would get a few more objects, basically because of 1, 1, but it's still relatively simple proof. The way that Apollonius is able to save some steps in this one is that he's able to move 2 of those lines out of the construction into the proof. So once again, the construction consists of a flat application of postulates, or if you will, abstractions of the use of a compass and a straight edge, so it could then also be applied to making actual construction. So Apollonius is again using only lines and circles, removing some constructions from the problem construction into the proof construction. And once again, we're going to have to kind of prove a number of these congruencies that are from the ground up using the properties of circles, because we haven't introduced an equilateral triangle. All right, so what I want to do now is discuss the way in which Proclus describes Apollonius's construction of 123, point out how that is somewhat difficult to accept on the surface, and then argue that in fact there's a simpler construction and proof which is exactly consistent with the construction and proof that we saw for 110 and 111. This is what Proclus says about Apollonius's approach to 123. He says, "We do not agree with the proof of Apollonius as requiring things which are shown in the third book. For the latter, having taken an arbitrary angle, angle CDE, in a straight line AB, with center D and distance CD draws a circumference CE. And in the same way, with the center A and distance AB, circumference BF, and having taken BF equal to CD, he joins AF." And that's the end of the construction. And then this is what Proclus said. He declares that the angles A and C are equal because they stand on equal circumferences. And that would imply a proposition from book 3. It would imply 327, equal angles stand on equal circumferences. And then he makes some other comments. It must also be taken that AB is equal to CD. I think this is actually said in the text itself, but he points out that that's the case. But basically, he says we consider such a construction because it involves taking things which come later as foreign to the elementary exposition. And we prefer, of course, the construction of Euclid. So Apollonius's construction or description here is much looser than in the previous two. It doesn't have the kind of mathematical detail for understanding what's going on. And it seems to imply that Apollonius is using 2 propositions from book 3. So let's first of all look at what Euclid actually does, and then we'll try to understand what Proclus is claiming Apollonius does, and then I'm going to give a reconstruction of what I think is a better way of understanding what Apollonius is up to. So this is Euclid's construction of an angle equal to a given angle at a given point on a given ray. we start out with angle DCE as given, and we have ray AB as given. And the first thing that we're going to need to do is take a random point on CD and another random point on CE, and then we join that line DE, and then boom, we're going to make a triangle congruent to a given triangle, which was just shown in the previous proposition. But if we flesh out everything which is involved in that, particularly carrying those lengths from the given triangle down to the given line, it involves 28 applications of lines and circles. So it's a very, very involved construction. And there it is. AF is the final line that we're looking for. So on the surface, Euclid's routine is very elegant. It takes a couple random points, draws one line, and then it applies a previously established proposition, 122, which is to construct a triangle congruent to a given triangle, given three given lines. But again, if we open up all of the subroutines involved there, we see all that mess of circles and lines that we saw in the previous figure. Now, as I mentioned, it's not exactly clear how Proclus intends us to understand Apollonius's procedure, but he definitely implies that it involves propositions of Book 3, and in particular 327. So let's sketch out this argument before I argue that there's a simpler argument underlying that argument. So this is what Proclus actually says. We draw a circle around D, passing through C with the random radius DC. It's going to pass through E as well. And then we're going to draw a circle around A with the radius AB, where AB is set equal to CD. So we have these two equal circles essentially. And then he tells us with BF equal to CE. It's unclear from the text whether this means the lines are equal or the arcs are equal, because it's just a feminine article, and either of those, there's no noun, so either of those nouns could be fine, but it's probably he means the arc. And then he tells us that the angles are congruent because they stand on congruent arcs. They stand on equal arcs. So that's true because it's proven in 327. So he's claiming that the proof relies on 327. But how do we know that those arcs are congruent to one another? I believe that the only way that we could know that those arcs are congruent to one another is if we cut off the length BF, the arc BF, using the compass. We first set the compass to CE, and then we carry it to B, and we cut off BF. And then we would know that the arcs are congruent because we would know that the distances are congruent. And if the distances are congruent, we would know that the segments are congruent. And we know that congruent arcs stand on congruent segments. This is demonstrated in 328. But it implies the simpler claim, which is that the segments are congruent. And if the segments are congruent, we don't need any propositions from Book 3 to demonstrate the theorem. So this is the way that I think we should understand what Apollonius is doing. He has the given angle CDE, and he has the given ray AB. And he takes the point at random on DC, and then he draws that arc through C and E. And then he takes the same distance, DB, and he carries it over to A, and he draws the arc that passes through B. And then he takes his compass, if you will, or his way of understanding the third postulate, and he sets the distance at CE, and then about B, he draws F so that it has the same distance. And then he joins AF, and that's it. That's the end of the problem. And that's, in fact, more or less the diagram that we see in the text. How would he prove this? Proclus claims he proves it based on the proposition from Book 3, but if this is the procedure that he used, there's a simpler proof. proof, of course, which is just that we join CE and then we join BF, and then we know that those segments are equal. And then we have side congruence to show that the angles are congruent. And we don't need any propositions from book 3 in order to show this. So if this is correct, then Apollonius's procedure would have been that we take a random point, we apply 3 circles, we apply a line, and then we move a couple lines into the proof. And then again, of course, as usual, we have to prove a number of things from the ground up based on the use of the circles. Then we apply the side congruent theorem. And if this is correct, notice that this argument follows the exact same pattern that we saw in 110 and 111. Namely, we're only using straight lines and circles, and any constructions that serve the proof are rigorously separated from constructions that serve the problem, and they're moved into the proof. And of course, again, the demonstration has to go from the ground up. So once again, the construction is more efficient than that in the elements, but the demonstration is less efficient. So presumably Apollonius produced this work in some kind of text that he wrote on the elements of geometry. And we don't know what this is. There are a number of titles of works that Apollonius wrote that are found elsewhere in the ancient tradition, and some people have claimed that this material comes from those titles, but really we have no way of knowing. But we can surmise, just on the basis of what we've seen today, that this was some kind of project in the foundations of mathematics, insofar as it was understood in the ancient period, involving constructions and thinking about efficient constructions and efficiency of proof, and so on. And if this account is correct, and it seems certainly the case for 110 and 111, and there's maybe some doubt about 123, but nevertheless, we can kind of outline Apollonius's approach. We can kind of give a rough account of what he was up to. First of all, in constructions, we only use lines and circles. We don't introduce fully formed objects into the construction. So we have postulates 1 and 2, or maybe it's a straight edge, it's not clear. We have postulate 3 understood as a transformation of motion, or maybe it's a compass, and we build everything from the ground up every time. We don't apply previously established problems as subroutine. There is some rigid transformation of length. We're able to carry this length around in the diagram in some way. This is some kind of axiomatic assumption of this constructive process. We have an abstraction of a normal compass, the way a normal compass works. Secondly, problem constructions and proof constructions are rigidly separated from one another. And any time a construction is unnecessary to the problem, it's pushed into the proof, presumably so that we don't need to use that object later on if we want to build a chain of constructions in some way. So all of these things together then allow the constructions to be more efficient, and sometimes radically more efficient. For example, constructing a square on a given line. So another thing which we see really only from the diagrams, it's not entirely clear from the text, but from the diagrams, it seems that Apollonius is interested in producing a kind of minimal graphic representation. So he's interested in using arcs of circles as opposed to whole circles, and so on. He's interested in not cluttering up his diagrams with unnecessary objects in the way that we sometimes see in other mathematical texts. But in general, the demonstrations are going to be less efficient and sometimes significantly less efficient. And this is because the properties of new objects are going to have to be shown from the ground up each time. We don't know, but we could also guess that probably Apollonius is able to point out, well, there's an equilateral triangle, so we're going to use the properties of equilateral triangles after he demonstrated this, and so on. But difficult to tell based on the evidence that we've looked at today. So we may have learned in school, and even now in some histories of mathematics, that Greek geometry is focused on constructions which are made with a straight edge and compass. This is just the standard account of the way the Greek geometry is described. One knows from histories of Greek mathematics that in fact Greek geometers use many more involved constructions in their more advanced work. They use conic sections, they use marked rulers, they use different types of machines, they use different types of assumptions about motion and so on. This is now well known to historians of mathematics. But what I'm also arguing is they appear to have had disagreements about even basic constructions in elementary geometry. So even claims about how we found plane geometry was in dispute. And in particular, I think I've established or shown that Euclid develops his problems using these routines and subroutines. So he introduces complete objects. And this is actually very elegant for the sake of the demonstration, because we can use the properties of those complete objects immediately in the demonstration. And also, it makes the routine itself quite elegant, because we don't have to build everything from the ground up. We can just introduce those objects. But there may have been little regard for how we actually draw these things. If one wants to draw a square on a given segment, Euclid's text is actually not much help for that. And so other mathematicians apparently took other approaches, and Apollonius appears to have been interested in producing routines that involve only lines and circles that are as efficient as possible using only lines and circles, which then probably could have actually been drawn with straight edges and compasses much more easily. I would have liked to see Apollonius' approach to drawing a square on a given line. But, then if that's the case, there's some efficiency which is lost in the demonstrations. It's clearly the case in some of the earlier demonstrations. Hard to know what would have happened later on. All right, thank you.